Great. Thanks for having me, Doc, and thanks for letting me to talk about this. I'm Mark Westlake. I teach at St. Thomas Academy in St. Paul, Minnesota. The high temperature on Monday in St. Paul is going to be -5. That's the high temperature. So,
I saw that the national wind forecast on Tuesday,
-17. So let me tell you why. Actually, I'll tell you why I still live there in just a minute. I've been teaching physics for 28 years, all at the same school, and we have an engineering program that unfortunately for all that time was left to the students that build our experimental cars. In 2017, we raised some money and wrote a grant to the E.E. Ford Foundation, and we were able to build an innovation center. So Carolyn Little, Carolyn, raise your hand. Carolyn and I got a lot of support. We built this innovation center so now all of our students can have that hands-on engineering component to what we do. In fact, our innovation center, we tell kids that if you can sketch it in a notebook, there's a pretty good chance that we can build it in there. We have that kind of equipment. So we're lucky, but we haven't always had that kind of equipment. For years and years and years, the things that we built were in the air conditioning chiller. We built things in my physics classroom, which meant that every day we had to put things away. In fact, Dr. Marks, I think you came to visit me one time while we were building our first solar car in the classroom. And we would have to put it away before we got started. So what I'm going to do today is I'm going to give you a little bit of history and talk about how the things that we thought were important as we went through aerodynamics, how to increase efficiency with all of our projects, may be important to you. Let's see if I can make this work. When it comes to making your car go farther, so there's some things that you can control. You can control the electrical efficiency, you can control the weight, you can control the rolling resistance, and you can control the aerodynamic drag. So I want you to keep that in mind as we go through this, and I'll remind you this in just a couple minutes. This is the very first thing that we ever built. Some students came to me in 1997 and said, we want to build a go-kart. I had no interest at all in building a go-kart, and I said, if you can find a contest that we can enter, we'll build something. They found the Minnesota Super Mileage Challenge. It was basically an efficiency contest. And I said, all right, we'll enter that because there wasn't much of a cost. And this is what we built. The inside of that is all just a steel frame. It's got a little gas motor, but we learned a lot about efficiency in our very, very first year. We took the car out without any body on it at all. And the car got 400 miles per gallon. 400 miles per gallon, just a steel frame and a 3.5 horsepower engine. When we put the body on that and took care of some of the aerodynamic ideas, that car got 800 miles per gallon. The following year we built this. That car got 1,300 miles per gallon. So you can see that there's a significant aerodynamic shape to that. As you go through and you start to design things, one of the things that we learn is that as cars get long, they release the air better. We always wanted the thickest part of our car to be 1/3 of the way back, and then 2/3 of it to be the trailing edge of it. As we moved along, I think in 2005, 2004, Dr. Marks contacted me, and I have no idea how you got a hold of me, but you said, would you like to build a solar car? And I was like, well, that's a big step to go from building these little tiny cars that get great efficiency to building a car that we race across the country. And it was that year, 2005, that the race went from Dallas, Texas to Pasadena, California. And this is the car that we built for that. This is when I decided I would always live in Minnesota. In Parker, Arizona, the temperature was 120 degrees. The air temperature was 120 degrees. I remember it being so hot that we had to douse the car in water to help our driving driver get back into it because it was so hot. It was 100 and Tarzan can't take that kind of heat. All right, it was on that day I said, I don't care if my eyelashes freeze together every morning, all right, when I go outside. All right, I'm never living in a place where it's 120 degrees. You can see that in this case, what we had done is we looked at tons and tons of different solar cars. And remember, this is still, I wouldn't say it's early in the solar car history of all solar cars, but it's not really far along. We had watched the classic video, the GM Sun Racer video, over and over and over again to see if we could steal some ideas from it. And this is what we ended up with. That's a young me. I showed this to my daughter, Greta, who's a high school senior, and she looked at it and she said, my gosh, Dad, you've gotten fat and old. So I don't think that's a direct result of solar car racing. I don't think so. Our first car, we built our own solar array. I honestly don't know what I was thinking. I said, we're going to build something that's really aerodynamic, and the way to build it aerodynamic was to put the cells right on the car, because then we could deal with the curvature of the car and everything. Wow, what a mistake that was. Every solar cell we broke cost us about $6 or $7. We broke a lot of extra value meals, a lot of extra value meals, as we tried to get this car up and running. In the end, the array worked pretty well, but I don't think it was, the car worked really well because it was aerodynamic, not because we had a great solar system on it. The next year, we built the same body, we used the same body, but we added a wheel. We added a fourth wheel. This is a lesson learned from racing cross country. Right? It turns out that when you're going down the road, if there's an object in the middle of the road and you have three wheels, well, you hit it. All right? And it doesn't matter whether that object is a rock or a hole or a dead animal, all right? You are definitely going to hit it. Right? And we said, all right, well, let's see if we can avoid that. And we added the fourth wheel to our car. And we brought it back to Texas Motor Speedway. This was by far the best solar car that we had ever built. It worked really, really well. It was aerodynamic. It was relatively light. It ran on lead-acid batteries. It was in the classic division. And you can see that we added some fairings to the wheels. All of it with the idea that really the cheapest way to make your car more efficient, right, is to deal with those aerodynamic principles. You can see how thin it is from the front as they went, so not much frontal area. You can see those wheel shrouds made a pretty big difference to that car as it went around and around and around the track. The next car we built was more of a novelty, I think, than an aerodynamic test. This was our solar commuter vehicle that we raced from Dallas to Boulder, Colorado. Right? Is that where we were? And the idea behind this car was to still work on some aerodynamic principles. In fact, the car itself uses a cam tail design where it tapers in to release some of the wind. But it has this trailer that you could take off and drive it without the solar trailer. The idea the students had come up with was they said, all right, let's make a commuter car. One that you could drive to work and then take the array off and leave it plugged in during the day while you're at work, and then drive it home at night, just leave the array there. Come back the next day, plug it back in, and when you needed to take the array someplace else, you could hook it back up and drive. So it was actually an easy car to drive because you sat in a normal driving position, right? And a lot of times you didn't even have to have the array. Now, of course, for the race, we did have the array. When we built that car, we always built our cars the same way at this time in our existence. We took big sheets of polyurethane foam and we glued them around the body of the car. So you can see that's just straight 2-inch foam. We would sand it down, which really was a terrible process, where students would use sanding blocks and power sanders and sand and sand and sand. And they would go home and their parents would call me the next day and say, everything in our house is ruined because they've been sanding this polyurethane foam. This led to some byproducts. Right? When you leave students unattended in the garage, they build stuff, and it's not always the stuff that you want. One of my favorite things here is the Nintendo remote that they built. I mean, what possessed them to do that, or build a foam screwdriver, or the foam handle, or the foam sandwich? All right. Now, this student actually, it turned out okay. This is Matthew Mikowski. He just sold his company to Zillow for $35 million. So he's okay. When we got to this point in the car, we always cover it with whatever we can get. Sheetrock mud in this case. We built a fiberglass mold of it. And you can see in this picture right here, these are the parts of that car. This is the actual model of the car, the buck, the plug, they call it. This is the fiberglass mold. This is the carbon fiber part that we pulled out of that mold. So that car is really pretty light. There it is with the array taken off with its umbilical cord. That was a really funny car. Yeah, in fact, we got a lot of media attention at home, maybe even more than on the race. Because our students would drive that around the neighborhood and people were amused that they could just plug it into this infinite source of energy. When we make the carbon composites, once we have the fiberglass mold, we really just vacuum bag them in the mold. Now the process is not super hard. Now I know one of the things that some people had talked about earlier was panels, carbon fiber panels. We do all those in-house and it's really, really easy. Anytime that you want to make a panel for your car, don't spend $1,000 and order it from someplace else. When we can show you how to do it for a couple $100. And all you need is a vacuum pump and a little bravado, a little bravery to go through and do that. So, this is when we decided to go back to the Solar Car Challenge. Now this is the start of Carolyn Little's existence with our program. In 2008, Miss Little got her room moved next to mine. She didn't have a choice, they just put her there. She was the French teacher at that time. And as we worked on the car in my physics room, we made a tremendous amount of noise and mess and smell. And she would come over and go, "What are you doing?" Because she's trying to teach French, which is like a more fancier subject than what I was trying to teach. And she eventually got connected to it and became one of our moderators. And I think this is the first car that you worked on with us. When we built this car, we didn't have any money. We were out of money. I had spent all of our money. And one of the things that Carolyn Little did was help us raise some money, but not necessarily for this car. So we said we're going to build a car for less. We're going to build it as inexpensively as possible, but still build a car that was really efficient and competitive. And we set that mark at $10,000, I think, that's a lot of money. But in solar car world, that's not a lot of money. So here's our retail price list here. You can see we actually came in a little bit over that. We were at about $11,000 for this car. Most of that cost was picked up by our sponsors. All right, either with cash donations or gifts in kind or just regular discounts on stuff. I'm going to stop right now and give you a big hint. If you need stuff for your solar car, like a PowerPoint tracker or electrical equipment, when you call the company, never talk to a salesman. Don't ever talk to a salesman. Always ask to speak to one of the engineers. And then when you get the engineer on the phone, you explain to him what you're doing, and then you say, do you have any that have scratches or dents in them? Do you have a test piece that we get? Because they always have a ton of these pieces of equipment sitting around in their shop, all right, with no place to go. They sit on the shelf and eventually they throw them away. So we've gotten tons of equipment from places simply by saying, can we have the one that you've been using to test? all right, and sent them to us really for free or a big discount. This car we made with just shrink wrap and foam core. Foam core is an amazing building material. Right? Foam core, that same stuff that you use for like the backdrop on science fair boards or for history day projects. We made all of this car with that. The next time we were at the Solar Car Challenge, we entered the electric division, the battery electric division. This is the car that we built. And that was when the rule was, I think, Doc, I think the rule was that the cars had to be 1.5 meters tall. Now they're shorter, is that correct? Yeah. So this car is just tall because of that rule. But it may have been my favorite solar car that we've ever built. All right? For lots of different reasons. I loved that it was the first year that my son was involved in the program. I loved that two people had to drive the car at the same time. I loved that you had to stop at these pit stops and you had people running your solar array trying to figure out how much energy was going to be available for the car when it came in, and you had to make decisions about when it came in, when to change the batteries, when to send it out. And I loved that William's team, all right, was super competitive. I mean, I think during that whole race we were always within a few laps of each other, which made the event even more fun. When we built this car, a big piece of it was, most of it was carbon fiber. The shell of that whole car probably weighed about 35 or 40 pounds. So which is pretty light in terms of that body. This was our solar charging station for that event. It was from this event that I got a phone call after we got home from my friend, Dr. Marks. He calls me up and says, Mark, National Geographic is looking for strange commuter cars. And I said, well, we have one. And Dr. Marks gave our information to National Geographic because they were about to promote a new video series called Breakthrough. And we said, hey, we want to be involved. So they called us up, we sent them some pictures of our car, we got the recommendation from Dr. Marks, and National Geographic says, we want you to bring your car to New York City and drive it around for a week. This is the only task. So we send our car to National Geographic, they wrap it in this really cool breakthrough wrap, and it's basically us, a school from Germany, and a school from Canada, right? And there's like 8 supercars, like an Audi A8, there's a Lamborghini, there's all these cars that they've wrapped. And the idea was hilarious. The idea was that we were going to drive around New York City, and when people called for an Uber, right, if they had a special code, then either one of these supercars or us, we're going to pick them up and drive them to their destination. This is by far the stupidest thing I'd ever heard of. So when we get there, we're like, we can't pick up people in this car and drive them around in Manhattan. I mean, you just can't do it. Even though we had a squire, a minion from Uber, whose only job was to follow us around in this SUV and make sure we didn't get run over, right? So here we are driving around New York City. We didn't have to pick up anybody with the Uber. I had that called Uber. They left that for the supercars to do. But it was pretty cool. And people were super nice. We thought, oh boy, people are not going to be happy seeing us drive around and take up space. But when we stopped at stoplights, people will get out of their cars and come over and take pictures with us. And for really four days, they paid for everything. So they paid for our hotel, they paid for food. I'm in my room one night, I get a call from the desk. They're like, there's some students down here that charge ice cream to your room every night. I said, I don't care. National Geographic's paying for it. And it was actually kind of a cool experience, all because of the Solar Car Challenge. So, one of the things that we built that was not aerodynamic, but I put this picture on here because honestly, this is my favorite thing we've ever built. we host an event called the National Indoor Electric Ice Race. All right, everybody got the same electric motor. Everybody had the same electric potential. So you get 24 volts, use like a little 400 watt motor. And we raced short track style on our ice arena. It was hilarious. People came from all over to do this event. We only did it for a few years. But this little lean trike that had spikes in the tires, oh, it was super fun to drive around on the ice. And it went fast enough where you could get yourself into trouble really quickly, right? If things didn't go up. No aerodynamic principles here whatsoever. Since then, we've been to the Drivers' World Championship in London, England, which was pretty cool. We had a chance to race against some of the top universities in Europe and in Asia. In 2017, we won the event. And the coolest thing about winning the event was that we got a week-long trip to the Ferrari factory in Maranello, Italy. All right, so our students got to bring their car to Maranello. They got to drive it on the Ferrari test track with the Formula One drivers. And Carolyn and I rode their coattails all the way. So super cool. And I put all of this all dates back to Solar Car Challenge. So what have we learned since then? Well, we know that there are still those same 4 things that we can control. No matter what we build, those are the things that we worry about. And we always know that the cheapest way to get the most out of any of our cars is to build them as aerodynamic as possible. So, here are some numbers. You can have 10% more solar power, and it'll give you about a 4% increase in performance. Solar cells are really, really expensive. And to go up 10% in power is really, really hard. 10% less drag gives you about 3% increase in performance. Rolling resistance, you can see about 1.3%. And even making your car a lot lighter doesn't have a huge effect on the performance of your solar car. When the University of Michigan won the American Solar Car Challenge, I think they were 100 pounds more than the next nearest car, but their car was super aerodynamic, and that ended up being what decided that event. So, what I'm saying is that if you're going to spend time and money, spend it on making your car aerodynamic. So, some areas that you can improve things right along the way. Electrical efficiency. People have already talked about this. Choosing the right wires for the job, making sure that connections are solid. You know, one of the things that we always do is we always bench test everything. We set up our whole electrical system on a bench. We take an infrared camera. We go over the whole thing, looking for anything where we might have a loose connection. So, or wires that are getting worn, because that's just a waste of energy. We choose the right gears. This is one of the things that we've seen in a number of cars over the years that have surprised me. It doesn't matter what the event is. I know that we all want to believe our car is going to drive 50 miles an hour for the entirety of the event, but the truth is most of the time those speeds are much lower than that. 30 miles an hour, 25 miles an hour. And electric motors love to run wide open. All right, very high RPMs, all right? And when you gear your car so it can run at those high RPMs, the motor becomes more efficient. If you get the motor specs for your motor, that's what you will see, is that as the RPMs go up, the efficiency also goes up. So this system right here, I think this is the one that we used in that orange solar car. We geared it for 30 some miles an hour, 36 miles an hour. I think we averaged somewhere around 30 miles an hour for the event. That's a 48 volt system. We had a 15 tooth front gear and a 70 tooth rear gear. So choosing to gear things correctly for the event really makes a huge difference in how much energy your little motor uses. That motor, that's a Briggs & Stratton E-Tech motor. You can still find them. I know, William, you used one of those for years, right? If you look on eBay, they show up every once in a while. The robotics guys still love them and try to snatch them up right away. But I'll tell you, those little E-Tech, Briggs & Stratton E-Tech motors are bulletproof. I mean, we've over-voltaged them, under-voltaged them, they don't seem to care. We've run them for years and years and years. Never changed the brushes in them. They're pretty efficient for a brush electric motor. You can hook it up to a golf cart controller, and really it works really well for not much money. So,
just aside real quick. Like Mark said, this E-Tech motor has really been out of production for probably over a decade now. So there are similar pancake motors out there that you could just look at and it's like, gee, that looks like that picture. And you can find, I think Perm PMG 132 is an example of that. So don't think you have to go to eBay and try to find this E-Tech motor. There are other options.
Yeah. It just works really well. And really, in the big picture of solar car racing, having something that's durable and is going to run all the time, that's a huge benefit for your team. We've built some things that are really light in the past, sometimes too light. The car that we built here, maybe it was too light. In fact, you can see our friends from Houston, Mississippi had come over to help us weld the part that had broken because it perhaps was too light. So don't go to the far end of weight. In fact, build it so that it's durable. That'll make a much bigger effect on your performance at the racetrack than trying to build something that's super light. Roll-in resistance, these are all things that I'm pretty sure that you know. We take all the grease out of all of the bearings in every bearing on our car, and we replace it with a light oil. It probably doesn't make a huge difference, but it's impressive when you spin the wheel and it spins for a long period of time. But really, simply by putting a little bit of oil in those bearings every morning, at least it feels like it makes a big difference. We found a number of different tires that we've used along the way. I think when we first started racing solar cars, we used kind of thick BMX tires. There's better tire options out there nowadays. If you can actually find solar car tires, I know Bridgestone still makes them, and you can still find Michelin ones. The Michelin ones are really hard to get. In fact, the last time we wanted to get the Michelin tires, Carolyn, who speaks fluent French, had to write a letter to Michelin in French, and they developed some crazy relationship, and we were able to eventually get the tires. If I would have written them the email, they would have said nothing. We wouldn't have responded. So let's talk about the main idea here. How can I save you some money and make your car significantly more efficient? So aerodynamic drag. I love this picture because it really describes drag the best possible way. It's not as important how you enter the air as how you leave it. Right? What happens behind your car is a much bigger problem than how you're actually entering and pushing through that air. This is a great picture of a solar car. I don't know if it's a real solar car or just a mock-up of one. But you can see the airflow over and around that car is very smooth. In this graph, there are two vehicles. One, this yellow line is regular bicycle. Regular 10-speed racing, I suppose now like 16-speed racing bicycle. The green line is a fully enclosed bicycle, one that has a body around it. And you can see at the speeds that we're going, let's just take 25 miles an hour here. This is around 140 watts of power to make that object move. Something that is just an exposed bicycle takes almost 3 times as much power, all right, to keep it moving. Well, a lot of that is because when you're talking about how objects go through the air, there's some principles involved. One, the shape of the object, right? What the air is like that day, whether there's a lot of humidity in the air, whether the air is hot or cold, those kinds of things. And you can see some basic shapes. One of the things that we do is try to take care of parts of the car that are exposed to the air. So one of the things we do a lot is we build fairings around things. So this is the formula for aerodynamic drag. It's not super important. I mean, you can look that up anywhere. But I used it to make some calculations in a minute that you'll be able to see. So here's some basic shapes. If you look at something that's round here, the drag coefficient about 0.47. As you get down to a streamlined body, right, it's about 1/10 of that. So significantly less drag as you go through the air. So if you look at a round tube here, even though it's not really round, a little bit oval, you know, the drag is about 1.1. When we get down here, it's 0.15, about a sixth, seventh as much drag. So where does that make a difference? Well, I love this picture of a barn owl and how it enters and leaves the wind. Some places that I look for ideas. These are two great places, all right? The crazy people at the eco-modders, if you just type in eco-modders, these are people that are taking their automobiles and doing crazy things to them to hyper mileage them, right? And some of the things are good. Some of them are literally just crazy. All right, but they have a website, ecomodder.com, and you can go on there and get all these ideas about how to increase the aerodynamic efficiency of your car. They also have some ideas on putting a new motor in it and stuff that's not realistic. The other one that I love, though, is the International Human Powered Vehicle Association. That's what this picture is from. And these are the guys that build bicycles that are trying to set land speed records. When you're trying to build something that's going to set a land speed record, aerodynamics is everything, right? Because you only have X amount of power, all right? A human can only put out a certain amount of watts, all right? So everything comes down to making sure that whatever you build goes through the air efficiently. So is there anybody here from the East Beast car, the East Wiley car? I love that they eco-modded it, all right? So I love that they took and they added this whole back section on to make the car more efficient, just like somebody had done with a Honda Insight. Now, the guy who did the Honda Insight, he claimed that he had a 13% increase in efficiency. 13%, that's a lot. You know, in a race that has, 400 laps in it, I mean, that's 45 laps. That's a significant increase simply by adding something crazy on the back of your car. We've done a number of inexpensive solutions. This is our friend. These are our friends from Houston, Mississippi. We see lots of solar cars that look like this. All right, that have a driver's compartment. They have a solar array that covers the top of the car, and they have some posts that stick up and hold up that array. I'm going to move over here, sorry guys. All right, lots of cars look like this. I will tell you that these poles that hold up your car are terrible aerodynamically. How terrible are they? Well, one of the things that we've done is we've made these fairings for the tubes. Somebody went in, one of our students went in and said, all right, let's take all of the tubes that are exposed to the air. We're going to make these little fairings for them. And we 3D printed them. I think we did this in On-Shape, all right? So for like a 1-inch tube. So we're going to use that as our reference. So if you have a 1-inch tube going up to the top of your car, how much drag is that just 1-inch tube? So I did some math. All right, so if we have a round tube, this is the drag force on it, right here. A 1.5 newtons compared to one that has that funny fairing on it. So we're just stick it on there with double-sided tape, right? For a 1 meter long tube. When you start talking about a race, when you get down to the bottom here, this is for 300 laps. To drive one round tube through the air is 1,086 kilojoules. So over 1 million joules of energy gets spent just driving that 1 meter long post through the wind, compared to the significantly less amount of energy it takes for one that's fair. So if you were to take just 4 tubes holding up your solar array, and that's a significant savings. To just drive those tubes, those 1 meter long tubes, 1 inch round through there, it costs you solar cells. All right. So in this case, I think when I did the math, it was about 4 solar cells at 20 miles an hour, and about 6 solar cells at 30 miles an hour, just for the tubes that hold up your solar array. So one of the things I tell teams, I tell my students, is think about energy in terms of your solar cells. Each solar cell, a really efficient solar cell is around 3.6 watts. Is that right now for like the sun solar, about 3.6 watts. So, I mean, any time that you can use 3.6 watts to make your car go faster, rather than drive a metal rod through the air, that's a win. So one of the things that we do is we build these wheel fairings. You can see here's one that they built for this car right here. Some things that we used to make that, we used some foam core, we used some razor blades, we put some slices in it. You can see where we've just sliced it and bent it around and literally hot glued it to the shape that we wanted. One of the things that we did with this car is we covered it with some carbon fiber, just a thin layer of carbon fiber. We let it sit. We squeegeed out the extra resin, sanded it down, and painted it. It wasn't very fancy. Didn't put it in a backing bag, didn't make a mold, anything. All we did was took foam core and we covered it with carbon and let it sit. You can see what those pieces looked like as they were drying. We did put some attachment points on the inside wherever they were going to be mounted to the car, just to add a little bit of strength to the foam core. But we cut those shapes really to length at that point, which is a regular jigsaw. Same with the tops. Once we covered it, once we had it all covered, we take some body filler, prime and paint it, and put it on the car. We built a whole car from foam core 1 year. Right after COVID, we were scheduled to enter an event. We worked very hard on for the NASA Rover Challenge, and got canceled. We had about a month and a half to build a car for the Minnesota Super Mileage Challenge, something that we hadn't been back to in 20-some years. And we were like, all right, we'll do it. And so we have no time. We have a frame of a car, but no body. We decided, all right, let's take our foam core to the extreme. Let's see what we can do by just taking foam core and putting slices in it and then covering it with vinyl. So this is the car that we built. And you can see how we started. We took the frame, we put slices, we were trying to be clever with how we put the slices in the foam core, and we just sliced through the top layer, the paper layer, and then crack it open. All right, so you can see what it looks like. We kept adding more and more until we ended up with this. That windshield is not anything more than a flat piece of plastic that we cut in that shape and then put it in there with some fasteners. So you don't need to get a fancy polycarbonate bubble in order to help yourself be more efficient. You take a flat sheet of plastic, just literally bend it around something, not even heat it up, all right, in order to make things more efficient. We took it then, and I think that we put stickers on, a lot of vinyl stickers. We had one student who thought it was hilarious to put the stickers on, so we let them do it. I do have to laugh at this picture though, because the uniform that my student, I teach in an all-boys military school. And this must have been a class A1 day. I don't know what we were celebrating that day, but they look like milkmen in their all-white uniforms. And I'll tell you the funny thing about teaching at an all-boys school, the days that they're in their all-white uniforms, they wear the funniest boxer shorts that they own, right? Because you can see them through the white pants. This is like a badge of honor for them. I don't get it. So we've also used shrink wrap. I know that a number of cars here have used shrink wrap to make objects more efficient. I know that Dr. Drago this morning talked about some sources for it. It's super easy to use. So, you know, as we went through, we built a frame, we took the shrink wrap. He said that it was used to cover loads when people are trucking down the road. I always think about in Minnesota, they pull all of the boats out of the river or out of the water in the winter, and then there's companies that just shrink wrap the top of the boats so that they're not exposed to the element and the snow just falls off. So we were able to get some from a company called Big Shrink, I think, that he had mentioned that this morning. We just taped it on. You can see that there's taping it on there. And then we heat it up. We used a gun, a propane powered gun, and it just pulls everything tight. And you can see how nice that fits on there. This is what that gun looks like. If you ever need to borrow one, let me know. I'll mail you ours and you can use it and then just send it back to me. It's fun to have a flamethrower. But you can see what that car looked like from the inside here with the shrink wrapped bottom so that we could help things be a little bit more aerodynamic. So that's what that finished car looks like. Now there's still some things about this that if we went back and did it again, I would change. I'm not really super excited about this very front part here, but really the rest of it was pretty good at releasing the air, and that car worked pretty well. So what are we doing now? This will be short. Right now we're playing with hydrogen fuel cells, which is kind of fun as an energy source. The hydrogen fuel cell that we have there is 1,000 watts. And really the only byproduct is a little bit of water vapor that drips out of the back. So you race other cars. It's an efficiency challenge where the idea is you go as far as you can on a cubic meter of hydrogen. The car that we built gets about the gas equivalent of 1,800 miles per gallon, which is pretty good. But we're starting to make our molds different now. We're 3D printing our molds. In fact, I know that the the Iron Lions, is that? Yeah, are also using a similar printer. So we print our molds. Here's a picture of the design, print them, put them together, service them, and then we make our carbon fiber parts in those molds. That's just the mold of the car. So it's all 3D printed on a giant 3D printer. It takes about a month to print all that. And that's what the finished body looks like when we pull it out of the molds and the finished cars. So for the event. So it's kind of fun. Do you have any questions? Yes?
What software do you use to make it?
So to make the cars, the car designs.
Yeah, exactly that mold.
So we did all of that in Fusion 360. So we used some surfacing software in it. There is some better software out there. There's a company called Rhino. And they're actually, the software that they have is not very expensive, but a lot of the people in the automobile industry are using that to design cars. So there were a lot of limitations in Fusion 360 to going through that we wish we wouldn't have had to deal with along the way. So, yeah. Other questions? Yes?
What's your input for that hydrogen fusion fuel cell? Is it already got hydrogen in it? Or
So we have a tank of hydrogen that we hook up to it, just compressed hydrogen, which you have the look that I had right away too. You're going to put a tank of compressed hydrogen, obviously flammable, in a car and have students drive it. There are a lot of safety systems in that car. All right, one is we have a hydrogen sensor in the back compartment of the car. There's vents above the driver, there's vents above the fuel cell, and it's got so many shut-off cylinders in it, so many solenoids in it that if there's one leak of hydrogen, the whole system just shuts down. So, the fact that we drive cars that have gas in the tank, similar problem. Yeah.
There's some
Yeah, you know,
This is first of all, so I wonder.
we have not done that, but I've seen that process. We just buy industrial hydrogen in a tank, and so hook it up and let it run. It actually works really, really well, to tell you the truth. It's surprisingly good system, even though hydrogen fuel cells, I think at this point, are about 43% efficient. That's a little bit more efficient than solar cells, right? I mean, solar cells are at 25 or 26 or so right now. Yes? So the question is it worth it to pay the extra for carbon fiber over fiberglass? Carbon fiber weighs a lot less. You need a lot less material to have the same amount of stiffness. How's that for an answer? I think by the time you have the carbon fiber and epoxy resin, which you have to use with carbon fiber, it's still expensive, but we use a lot less of it, especially if we're putting a core material in there. So for almost all of the bodies that we've ever built, not only is it 2 layers or 3 layers of carbon, there's a core layer of foam in there or a core layer of honeycomb, Nomex honeycomb, and that makes a huge difference, right? I mean, the idea is that the core layer is actually making it, helping make it stiff. Okay, I'll be around for a little bit, so let me know if I can answer your questions. My contact information is there. We would love to help you if we can. So we want to make sure that you're successful, and especially as you get into more advanced technologies, if you send me an email, I will email you back right away. So with whatever information you need. Doc?
Thank